All right. Good morning, afternoon, or evening, everybody. Welcome to the NASA Commercial Satellite Data Acquisition Program Vendor Focus Airbus webinar. This is your host, Jennifer Brennan. It is 2 p.m. Eastern Time, so we're going to go ahead and get started here. What I'll do first is begin today's webinar with a few logistics. To ensure the best audio experience, all participants have been placed in silent mode, but if you have any issues or you have any questions, what I'd like for you to do is enter those into the Q&A panel rather than the chat, and you should see that located on the right side of your screen. Today's webinar is being recorded. The recording will be posted to the Commercial Satellite Data Acquisition Program playlist within our NASA Earth Data YouTube channel. And usually that takes about a week, but it could be posted a bit sooner. Once completed, I will send an email to all registrants and participants that will include links to both the recording and presentation slide decks used within today's webinar. As far as timing is concerned, today's webinar will be 1 hour long with 45 to 50 minutes allocated to the presentation and live demonstrations. A 15-minute Q&A period will follow, and depending on the volume of questions that we receive, we may extend the Q&A session an additional 15 minutes from end time, but we will have a hard cutoff of 3:15 p.m. Eastern Time. During this afternoon's webinar, we will have, let me go ahead and advance my slide here really quickly. All right, during this afternoon's webinar, we will have one speaker from NASA's CSDA program and 3 speakers from Airbus to present the vendor content. Dana Ostrengo will be our first speaker this afternoon. She is the NASA CSDA project manager here at Goddard Space Flight Center. She will kick us off with an introduction to the CSDA mission and program goals, and also provide a brief overview of the Airbus contract and data access. From there, we will transition to our Airbus speakers. Our first speaker from Airbus is Jen Kennedy. Jen is the Senior Director of Sales for Airbus. She will kick us off with the vendor presentation with a brief introduction, and then from there we will transition to our second speaker, John Collins. John is the Director of Customer Success at Airbus. He will continue with a brief history of Airbus and an introduction. After this, we will toss it over to our third speaker this afternoon, Peter Barron. Peter is a lead for technical sales at Airbus. He will continue this afternoon's presentation by providing an overview of Airbus's optical constellation and products. And then what we'll do is we'll transition back over to John, who will introduce the Airbus radar constellation and elevation product suite. And then Peter is going to provide some information about how to access Airbus data through the CSDA program and via the OneAtlas tool. John will wrap us up this afternoon with some research use cases and some conclusions. And then after our last speaker has finished with his presentation, what we'll do next is we're going to move to the optional final polls and open up the question and answer session. And so before I toss it over to Dana, what I want to do is say just a couple of words about this afternoon's Q&A session. We will try to answer all of the questions within the time allotted, but if we are not able to address your question during the Q&A period, our speakers will be able to follow up with you offline. So with that, it is my pleasure to introduce today's first speaker, Dana Ostrenga. And so, Dana, I'm going to stop sharing my screen and toss it over to you to kick us off. All right. Thanks, everybody.
Wonderful. So sorry about that delay, everybody. And thank you, Jennifer, for getting us started today. Welcome again all to the Commercial Satellite Data Acquisition Program webinar series, where we are here to learn about Airbus. So I am Dana Ostrenga. I am the CSDA project manager at NASA Goddard Space Flight Center. If you missed any of our previous webinars, just to give a little bit of a background, the Commercial Satellite Data Acquisition Program, or CSDA, has the mission to focus on identifying, evaluating, and acquiring commercial satellite data that supports the NASA Earth Science Research and Application goals. So the program itself has 5 main goals. One is to establish a continuous and repeatable process to on-ramp new commercial data vendors. 2, to enable sustained use of that data for broader dissemination to our scientific community. We also want to ensure long-term data preservation, access and distribution of that data, ensuring scientific reproducibility, and also to collaborate and partner with interagency and international partners on the evaluation and scientific use of the data. And then last, to comply with the 2003 U.S. Commercial Remote Sensing Policy. If you've missed any of our previous webinars, here's a link on this slide that brings us to the playlist of all of our past vendor series. We completed our last IDIQ on-ramp 1 back in September, and this was a multiple award on an indefinite delivery, indefinite quantity, fixed price contract that was in response to an RFP that closed in March of 2024. The contract itself goes through November 2028. We've awarded 8 new vendors under this IDIQ on-ramp 1, which includes BlackSky, ISci, MDA, Pixel, Planet, Satellogic, Teledyne Brown, and the Tomorrow companies. So these 8 new vendors joined our previously awarded 7 vendors. So that means that right now on the CSDA program, we have 16 total vendors, 15 on IDIQ. Once they are part of the program, we'll evaluate their data, and then once complete, they'll be able to propose to competitive task orders. If they are previous vendors that have had a BPA agreement or a BPA contract and have already been evaluated, they can now compete under the IDIQ. And they can also bring in new products that can be evaluated before being provided as offering to the rest of the program or our stakeholders. So I talked about the evaluation and the contract. We have 2 types of contract vehicles currently with our vendors. One is that IDIQ, and the other is the blanket purchase agreements, which we're currently closing out in favor of the more competitive task order process. We've been building upon our collaborations with federal partners as well as our international partners when it comes to data assessments, new capabilities, and data sharing. We're also working to create a more efficient search and discovery of the data within our program for authorized users through our own program data portal, but also by integrating with NASA's Earth Data Search client. Our program is heavily focused on the continued assessment of the quality and utility of the data. So just looking at our vendors listed here in a reverse timeline order, we've kicked off the evaluation of Planet IQ and Umbra Lab data already, and we are currently in those evaluation processes. We've begun discussions with the PIs who will conduct those evaluations. We also have 4 evaluations that are either at completion or near completion from the BPA on-ramp 3 solicitation. That's GHGSat, GeoOptics, Capella Space, and ISci. All have completed evaluations in the debriefings. So the final reports of those evaluations will be made available soon, and the data that was acquired during those assessments, with the exception of ISci, will be available on the SmallSat Data Explorer, which I'll show in a moment. We've also completed the evaluation process for BlackSky and Airbus, which we're here to talk about today. Those were part of our original BPA on-ramp 2 solicitation, and then we have DSIS and WorldDEM data that was brought in through our pilot program and as part of the cooperative agreement. And we've brought in Planet-inspired data through originally a BPA task order and Maxar data via NGA. Airbus has been part of our program since December 2020 when they were previously awarded a blanket purchase agreement. That was to acquire SAR data for the purpose of evaluation. The evaluation provided not only a full assessment of the Airbus data, but also facilitated a joint SAR guidelines with ESA on criteria for SAR data. In October 2023, Airbus also entered into an IDIQ contract where they were awarded a 12-month task order in August of 2024 to provide SAR and digital elevation model data to the NISAR science team. That data is acquired from the task orders will be available also to those authorized users. And if you qualify for access under our licensing agreements, you can get authorization through the CSDA web form. And there is the link for the sign up. And you also here can see a screenshot and link of our SmallSat Data Explorer where you can search and access data as an approved user from all of our vendors. Data that is downloaded will continue to be integrated here and then also and made available through this interface. And then also, as I previously mentioned, available through the Earth Data Search client. So that brings us to the next portion of our webinar. Please welcome our first invited speaker, Jennifer Kennedy, who will talk to you further about Airbus. I'll stop presenting, and Jen, you can take it away.
Great. Thank you very much, Dana and Jennifer, for the introductions this afternoon. Good afternoon to everyone. We are very happy to be here today to present the Airbus product offering available today on the NASA CSDA contract. The Airbus team is focused on working with the research community to bring both optical and radar imagery, along with our various digital elevation models, to support scientific advancements in the respective NASA Earth Sciences focus areas. As Dana mentioned, Airbus joined the CSDA program in late 2020. We began with our initial offer of the radar imagery products and their derivatives, including the WorldDEM and the co-SSE complex data from the original tandem WorldDEM mission. We have since onboarded optical imagery from various constellations, including both our archive and tasking services. Our speakers today, John Collins, the Director of Customer Success, and Peter Barron, Technical Sales, will take you on a tour of the Airbus history, provide you a comprehensive look at the various product offerings available today, and demonstrate how easy it is to search and discover the Airbus data through the OneAtlas portal, while the ordering itself is actually fulfilled by the CSDA data management team. Finally, we will showcase how the Airbus data is being used by researchers today to support their studies. With that, I will now give John Collins the floor.
Thank you very much, Jen, Jennifer, and Dana. All right, so we will start off with a poll, with a little quiz, a little brain teaser to get people's brains working wherever you are in the world. We have a merged image here for you to take a look at, and we have 4 options where you think this might be. The 4 options are the North Island of New Zealand, Sumatra in Indonesia is B, one of the Hawaiian Islands is C, and the island of Honshu in Japan is D. And so what you're looking at here is a merged image of TerraSAR X on the left-hand side. That's the grayscale imagery that is the output of radar remote sensing. And on the right-hand side, we have Spot 6 imagery. So that's our 1.5 meter imagery that we collect. So yeah, let's see whether crowdsourcing can get the right answer here. So again, it's either in New Zealand, it's in Indonesia, it's in one of the Hawaiian Islands, or in Japan. So we're down to just a few seconds left. And yes, I will tell you that crowdsourcing worked this time. The correct answer, which was the majority people selected, is A. This is the North Island of New Zealand. And this is Mount Taranaki, sometimes previously known as Mount Egmont on the North Island of New Zealand. So good work with your geography skills, everyone. Moving on, Airbus. You've probably heard of Airbus. You've probably flown on one of our aircraft. You might have done some exotic or remote field work. You might have flown on one of our helicopters. So that's probably the Airbus that you're aware of, the Airbus you know about. But there is another part of Airbus that some folks are less aware of, and that's the space aspect of Airbus. We're the world's largest manufacturer of large format satellites. We do all sorts of different things with satellites. You can see there, Galileo 2nd generation is the European GPS constellation. Sentinel is a remote sensing part of the Copernicus program for the European Union, the European Space Agency, and Pléiades 1A and 1B pictured here are our own satellites. We'll have more about those later. And Airbus has really specialized in Earth remote sensing from the very start. So all of these satellites are satellites that we built for Earth remote sensing over the last 40 years. Even some of the newest ones, some of the Copernicus ones aren't even pictured here. So we've really taken it to heart as Airbus, helping pioneer commercial remote sensing over the years. And so here's just a little corporate history. You might have, if you've been in this community for a long time, back in the 1980s, the first subsidiary that was formed Spot Image, cooperation with the French Space Agency and the commercial world. Spot Image was the first commercial remote sensing company. Throughout the years, we've added more subsidiaries, we've merged, we've renamed ourselves a few times. Some of you may remember Infoterra as the radar remote sensing company out of Germany. But to this day, we all merged together and rebranded as Airbus in 2017, and now we are part of the Space Digital Division of Airbus. And yeah, we want to be your trusted partner for geospatial products and services. And so, yeah, under the names of those various names, we have launched a number of our own remote sensing satellites, starting with Spot 1 back in 1986, and continuing up with our first radar satellites in 2007 with TerraSAR X, and then Tandem X in 2010, and then more higher resolution optical satellites with Pléiades and Pléiades Neo. So we'll be going into more details about these the data products from these satellites in a few minutes. But we just wanted to round out the history part by talking about from the start, from when we pioneered commercial remote sensing in 1986. Two events happened rather at the same time. We launched Spot 1, and just a few months later, the Chernobyl accident happened. And this was the first time you were able to get commercial remote sensing behind the Iron Curtain, as it was then, looking at something that was otherwise inaccessible. These were 20-meter images, so not quite the resolution we have today, but we were able, people were able to confirm that yes, indeed, and there was debris on the ground, and an accident had occurred. Flash forward several decades, and this is what you can see from space. This is the Chernobyl site today, or at least a couple of years ago, with the new safe confinement building, which was built on top of the destroyed reactor. And here's a zoomed in picture of that. This is an HD 15, so this is a 15 centimeter resolution image, an upsampled image of the new safe confinement building. And we were intending to put these Chernobyl slides in to this presentation for the last few weeks. And then over the weekend, something interesting happened. There was a drone impact actually on this new safe confinement building. So we collected this very image and upsampled it to H15 just yesterday. Even the news today, we're able to collect and have imagery available for the global community. And so, talking about imagery, talking about data products, these are our data products that are available to CSDA users. So we're just putting this one slide right up front before we talk about all of these in detail. On the left-hand side are our optical products and our optical elevation products down there at the bottom. We have archive and tasking for all of these satellites and also for the elevation products. On the radar side, there's our 3 sensors that are in space, all the modes that are available, and all the tasking options for new tasking. And of course, we have the archive available as well. And at the bottom, we have all of our elevation products as well. So moving on, this is our second and actually last poll. So we get the Airbus polls out of the way pretty quickly here. We just would like to know generally if what sort of Airbus satellite imagery or data you would be most likely to use in your current or upcoming research. And so there's the 4 categories of imagery and data that we generally offer. We have the optical imagery at A, radar imagery at B, the SAR interferometry data at C, and digital elevation models at D. So if you could make your selection on the side there, I'd appreciate that. And this particular background image, we did manage to merge 3 of those 4. So on the top right, we have our WorldDEM product. And then on the bottom left, we have our TerraSAR X imagery. And then right in the middle there, we have a 30 centimeter Pléiades image where we are actually catching the lava flow here in Grindavik in Iceland. So There we go. All right. So thank you very much for your answers there. I appreciate you letting us know what you're most likely to use. And yeah, I'm going to hand over to Pete now, and Pete's going to talk about our constellations and about the technical information on our optical satellites. So over to you, Pete.
Thank you for that introduction, John, and greetings, NASA community members. So let's now get into more specifics about the Airbus satellite constellations and the geospatial products in this next section. Airbus owns and operates our own Earth observation satellites, specifically large format satellites that provide exquisite image quality and geolocation accuracy and some of the highest spaceborne resolution in the commercial market today. Airbus satellite constellation you see on this slide, currently on orbit, provides unique access to multi-source, multi-resolution, electro-optical, and synthetic aperture radar sensors, which allows our customers to monitor sites and give insights into man-made and or environmental context and conditions on a global level. Our optical satellites range from 30-centimeter resolution with the arrival of Pléiades NEO sensor 4 years ago, and it also includes our successful legacy constellation, Pléiades 50-centimeter and Spot 1.5-meter sensors. And we have our X-band radar sensors offering imaging modes ranging from 25-centimeter staring spotlight mode up to a wide scan 40-meter resolution. Next slide, please, John. And the Airbus strategy behind these constellations is all about choosing the right sensor and resolution for your project needs. Here you can see that Airbus has the ability to image multiple sensors on the same day with Spot 1.5-meter, Pléiades 50-centimeter, radar using the multiple imaging modes, and the Pléiades 30-centimeter satellite data in this graphic over Miami here. We offer optical and radar tasking options with multiple tasking modes for ultra-fast delivery. So we have optimized tasking plans allowing daily revisits over any place on the Earth, and we offer acquisitions regardless of weather or lighting conditions thanks to the radar constellation. And the aim of this constellation is to really make the link between resolution and image swath width. So we have the satellite that can provide insight from local level to nationwide mapping, from detection up to classification and identification. So choosing the right sensor really depends on the final application. On this next slide, we highlight some of the imagery at full resolution for each sensor. Our core offer is really delivering satellite imagery data, but users can also get a comprehensive portfolio of premium imagery, high quality elevation models, global reference layers, and innovative analytics. We also have a digital cloud-based platform called OneAtlas, where our customers can gain access 24/7 to the archive and tasking, which we'll speak about later in the presentation. Next slide, please. Now let's focus in on a little bit more technical details about the electro-optical sensors and products. The following chart shows the characteristics of all of our active optical sensors, Spot, Pléiades, and Pléiades NEO. There's one Spot satellite on orbit today, two Pléiades 50-centimeter satellites, and two Pléiades NEO 30-centimeter satellites. All of these satellites are situated in a sun-synchronous near polar orbit at their respective altitudes. All of these satellites are push brooms or linear array sensors, offering a long dwell time and better radiometric quality, such as signal-to-noise ratios. The orientation allows us to achieve daily or near daily revisit at about 10 or 10:30 local time. So Spot is able to capture up to 3 million square kilometers of imagery a day. Pléiades and Pléiades NEO can capture up to 1 million square kilometers a day. We've generated quite a large archive catalog over the years with all these sensors, specifically for Pléiades NEO 30-centimeter data, over 426 million square kilometers of data since 2021. With the Pléiades 50-centimeter sensor, we have over 1.9 billion square kilometers of data, and with Spot, over 14 billion square kilometers of data dating back to 2012. Next chart, please. This slide shows, this next slide, three slides, we'll get into each of the sensors in a little bit more technical detail. So this chart shows the Spot satellite specifications with a 1.5-meter true color image in the background over the recent LA fires. So Spot offers a 1.5-meter panchromatic or a 6-meter multispectral pixel resolution at nadir. It's got a very wide swath width at 60 kilometer, and it can image up to 45 degrees off nadir view angles. We can collect in mono, stereoscopic, or tri-stereo tasking modes, and we offer up to a 12-bit image depth at the respective spectral ranges listed here. Lastly, the spot sensor has 4 multispectral bands with various product combinations listed below. So we can deliver data as a bundle product where the panchromatic and the multispectral bands are acquired simultaneously, they're co-registered, and they're delivered separately. Or we can deliver a pan-sharpened product where we fuse the pan and the MS to create a natural or false color image. A link to the spot user guide will be provided in the PDF version of this presentation, which contains comprehensive info on the satellite and product specifications. The next slide shows the Pléiades satellite specifications with a 50-centimeter true color image over the recent Palisades fire in the background there. Pléiades offers a 0.5 meter panchromatic and a 2 meter multispectral pixel resolution at nadir. It offers a 20-kilometer wide swath, and it can, again, image up to 45 degrees off nadir. It can collect in monoscopic, stereoscopic, and tri-stereo tasking modes. And again, we offer up to 12-bit image depth at their respective spectral ranges listed there. And we can provide the same product combinations as Spot. Lastly, Pléiades also has 4 multispectral bands with those various product combinations. And again, the link to the Pléiades user guide will be accessible in the PDF version of this presentation. The last satellite technical spec chart here is for Pléiades Neo. It's showing a 30-centimeter false color image over the recent LA fires in the background. Pléiades Neo offers a 0.3 meter panchromatic or 1.2 multispectral pixel resolution at nadir. It offers the widest swath width of any 30-centimeter sensor on the market at 14 kilometers, and an impressive 3.5 meter native geolocation accuracy, which we'll go into a bit more detail later. It can image up to 45 degrees off nadir again. We offer mono, stereo, and tri-stereo tasking options and up to 12-bit image depth with the respective spectral ranges there. And again, we can provide the different product band combinations. Where Spot and Pléiades were 4 multispectral bands, we added 2 new bands on Pléiades Neo, which includes the deep blue or coastal blue for bathymetry applications, and the red edge for agricultural analysis. And again, the Pléiades Neo user guide, there's a link there that will be available in the final PDF. Next slide, John, please. This next slide talks about some of our tasking options. So as for tasking the optical satellites, we offer both standard and premium tasking options on the CSDA catalog. Both 1 day, the premium tasking option, and 1 plan, a more standard version. With 1 day, again, I mentioned this is a premium tasking offer, and we offer 100% assured collect on a specific day. 24 hours before your acquisition date, you receive a weather forecast to let you confirm, postpone, or cancel your request at no cost. With 1 plan, it's more of a standard tasking option. We will obtain a qualified coverage with an agreed time frame. You select your time frames, dates, preferred acquisition parameters, and we ensure you receive the right qualified coverage matching your project milestones. So whether you're dealing with long-term changes or highly dynamic situations, you'll get the required intelligence at the frequency you choose. For the higher frequencies, our cloud cover commit ensures you pay only for the most useful results. So commissioning a satellite and obtaining imagery has really never been easier through our Constellation. Continuing on, the next slide here, this shows the 4 most common acquisition modes. We offer imaging modes in a strip acquisition or in a strip mapping mode, or in target mode, and again in stereo mode. With strip, we can acquire very long image strips. With strip mapping, we can acquire multiple image strips in a single pass up to a 1 square degree automatically orthorectified and delivered. And then with target mode, which is really the most popular mode, we can collect multiple targets in a single pass over a 1,000-kilometer corridor within the 30-degree view angle. And again, we can collect in a stereoscopic mode in a single pass, providing dual stereo or tri-stereo source data. This next video shows how 1 satellite executes its acquisition plan on a single orbit over Europe. The satellite's maneuverability makes various acquisition modes possible, and it's adapted to a large range of mission requirements. So the standard north to south image strips, in this case for Pléiades NEO, the 14-kilometer swath width shown there, it'll be suitable for a lot of mapping applications, while target mode will fit a lot of defense intelligence and natural disaster and emergency requests. In addition to capturing single images, we can capture stereo pairs, which will allow us to generate digital elevation data like digital surface and terrain models and other 3D modeling products. So each of these satellites are extremely agile thanks to our in-house manufactured control moment gyroscopes, CMGs, and that enables the spacecraft to quickly slew left and right to collect one or more targets. So these are very agile satellites. With these commitments to deliver new imagery collections over your area of interest and our OneTasking plans, we can support really any situation from basic map updates to emergency response. Next slide, please. The next slide shows our standard processing levels, and they're produced automatically in our production center. We offer 3 different geometric and 3 different radiometric processing options, from least to most processed, to meet more advanced user needs and or to display image-ready formats for new users. With the geometric processing options across the top, we offer primary, projected, and ortho. Primary, also called perfect sensor or restored sensor, is the least process and refers to an image with no cartographic projection. Primary product is optimal for users familiar with satellite imagery processing techniques wishing to apply their own orthorectification or modeling. With the projected or ortho-ready, this is georeferenced or resampled on a cartographic projection at a mean ground elevation. The RPC files will be included with both the primary and projected products, which gives the user the physical information needed to produce an ortho rectified product. And finally, the ortho is the most processed geometric processing level, and it refers to a georeferenced image in Earth geometry. It's corrected from acquisition and terrain off nadir effects with ground elevation provided by a digital elevation model and or ground control. This product may then easily be superimposed on a map. The 3 radiometric options below, basic, reflectance, and display, are simply, again, from least process to most process. Basic being the least process, where the imagery corresponds to raw data without any atmospheric correction. The absolute calibration coefficients are provided in the metadata file, ensuring the spectral corrections from space to ground by the user. The basic values are maintained in their original 12-bit for depth for use in most spectral applications. The reflectance imagery is radiometrically corrected from sensor calibration and systematic atmospheric effects using a molecular or Rayleigh diffusion. The image values are provided in a normalized reflectance values with a 1 to 10,000 ratio. These reflectance values are maintained to the original 12-bit depth and also for bit-oriented format, as geotech needing a 16-bit integer storage. The reflectance products prepares users for spectral analysis work. In addition, the reflectance products provides a lookup table for true color rendering. And finally, the last radiometric option is display, and it's the most processed where a true color curve has been applied to the image. The imagery values are 8-bit numbers optimized for direct rendering on the screen or visualizations. The values are not reversible to spectral physical unit. Next slide, please. Here you can see a 30-centimeter image over Sydney Airport in Australia. And this is a Pléiades NEO 30-centimeter image. Pléiades NEO really has the most accurate geometric accuracy of all Airbus satellites. The Pléiades NEO data offers a first-rate ground sampling distance of 30 centimeter combined with a native geolocation accuracy of 3.5 meters, CE90. The geolocation accuracy refers to the precision with which the location of an object in the image matches its ground location. And an accuracy of 3.5 meters CE90 means that 90% of the image point falls within 3 meters horizontally of their absolute location on the Earth's surface. So the combination of spatial resolution and geolocation accuracy makes Pléiades NEO one of the most powerful and versatile surveying and mapping satellites ever built for commercial use. We also integrate our own reference layers, such as WorldDEM, space reference points during ortho production to achieve impressive planimetric geolocation accuracies worldwide. And finally, the plot chart on the left there, which shows the horizontal error of the Pléiades NEO ortho near infrared band was taken from a recent USGS characterization report of the Pléiades NEO sensor. And so we'll include a link to this USGS report in the final PDF, which summarizes in great detail the geometric, radiometric, and spatial performances for both Pléiades NEO imagers. Next slide, please. Here's another Pléiades NEO image of the Statue of Liberty, but this time in high definition, 15-centimeter rendering, as mentioned earlier in the webinar with the Chernobyl example. HD15 is simply a resampling of the native 30-centimeter imagery, and it's produced by applying a deep learning, an AI model, that increases the sharpness of the details while maintaining the integrity of the original data. So due to Pléiades NEO impressive radiometric qualities, such as signal-to-noise ratio and modular transfer function, we can take advantage of this image sharpening, which offers improved visibility of small objects and linear features. Our cutting-edge technology really ensures consistent and reliable results. This HD technology intelligently increases the number of pixels through a complex mathematical model that is tuned to a specific requirement of our imagery, resulting in superior visual experience. The innovation will produce well-defined features and help both people and algorithms better extract meaningful information out of the imagery. While this resampling or transformation does not change the original ground sampling distance, it sharpens the image and improves the clarity on linear features such as building edges. HD15 is currently available in both primary and orthorectified geometric processing options. And my last slide for this section, just to wrap up, is Airbus will continue to invest in the future of very high resolution data. The follow-on Pléiades NEO program will ensure the continuity of very high resolution satellite imagery with 20-centimeter class GSD that's launching in the next few years. This data will offer the same exquisite class imagery as the existing Pléiades NEO constellation, but with better resolution, increased capacity, serving more customer needs, and boasting stronger constellation reactivity. So Pléiades NEO ensures service continuity for many years to come, at least up to the year 2040. At this point, I'll hand the microphone back to John to speak to our radar constellation.
Thank you very much, Pete. Yes, so I'm going to talk about our radar constellation and the data that comes from that constellation and is available to CSDA users. So here is our constellation of radar satellites. We have 3 radar satellites, 3 X-band radar satellites in orbit right now, TerraSAR X, Tandem X, and Pléiades. As you can see from this little image here, TerraSAR X and Tandem X orbit together. They actually orbit really, really close together. They're separated by just a few hundred meters in space and actually have been orbiting that way for well over a decade. The reason they orbit like this is that they can do single pass interferometry, and this helps produce our products like WorldDEM, our global elevation model, which I'll talk about in a second. Pléiades operates 1/3 of an orbit away from the other 2 satellites, but essentially we have 3 satellites in orbit, but they operate as 2 satellites because TerraSAR X and Tandem X are so close together. The normal target revisit time at mid-latitudes is every day and a half. So at mid-latitudes, you can get an imaging opportunity every day and a half, and at upper and much lower latitudes, you can get an opportunity every day. The interferometry repeat cycle is an important aspect for anyone who is doing repeat pass interferometry. So this is where these satellites are in orbit every 4, 7, and 11 days. They are on that schedule in the identical place in orbit every 4, 7, and 11 days. And this is very important for interferometry because you really need to have the satellite in the same XYZ location in space in order to take your new image collection, your new data collection, so that you can build a stack of images to do your interferometry on your area on the ground. So with two essentially satellites in orbit, we reach that every 4, 7, and 11 days. The resolution of the satellites goes from 25 centimeters up to 40 meters. I'll go through that more of our acquisition modes in a second. And in the archive, we do have more than 640,000 radar images available for you to use, including data stacks that other people have built up over the years. So if you're interested in interferometry, it could be that your area has already been collected by somebody else in the past. So this includes data collected in all 6 modes since 2007. Moving on, again, talking about interferometry, it's important to talk about the precision. I talked about the 4, 7, and 11-day repeat cycle for interferometry purposes. But the other thing that's important to know is the precision of the orbit tube, as it's called. So we've done our best to make sure that all 3 satellites are in the same place in orbit every 4, 7, and 11 days, but we've done this consistently over the decades. And so this means that if you are collecting data for interferometry purposes, you will have this consistent orbital positioning for not just a few months, but over the years. And even more important than that, the orbit ephemeris information that is required when you're doing interferometric processing can be as accurate as 10 centimeters. So we're able to place any one of these 3 satellites to within 10 centimeters in space using our science orbit. That does take a few days after you get the image. For security reasons, the science orbit is held back for a few days, but then you can get that and position the satellites very precisely to within 10 centimeters. Or you could use the 2-meter rapid orbit, which arrives when your imagery or data arrives. It's also very precise, but yeah, we can get as close as 10 centimeters ephemeris information, location information. Next slide talks about our collection modes. From the left-hand side, these are the lowest resolution. To the right-hand side, it's the highest resolution. Unlike with an optical satellite, with a radar satellite, you can focus the energy over a smaller area and thereby getting a higher resolution in the imagery. So if you're looking just to monitor over the ocean, then wide ScanSAR or ScanSAR are the sort of optimum modes for you. It allows you to get tens of thousands of square kilometers in a single pass. If you're doing maritime monitoring, we do have a maritime monitoring package as part of our offer, and that includes data in the 40-meter and 18-meter resolution. On the far right-hand side, with staring spotlight and high-resolution spotlight, we have the much higher resolution. And of course, when we focus the energy over a smaller area, you get a much smaller image. So you're able to get a 25 centimeter imagery, but it's really over a 4 kilometer by 4 kilometer square. The majority of people who use TerraSAR data tend to use the 1, 2, and 3 meter resolutions. When you dig into the archive, you'll see that the majority of acquisitions are in the 1, 2, and 3 meter resolution range. But of course, if you're ordering new data, you can specify anything from 40 meter down to 25 centimeter for new acquisitions. As with our optical data, we do have some processing levels for our radar data. On the left-hand side is the least processed, the SSC, the single look slant complex range. If you're doing interferometry, you want the least processed data, so you would order SSC. As we move to the right, we add elevation models, we orient the imagery to the ground, and we essentially add more background information to allow you to tie the imagery to the ground. So the most processed level is the enhanced ellipsoid corrected, the EEC, and that's if you're doing topographic mapping or something like that, and you want to know that there's an elevation model behind your image, and that everything you see on the image is tied to its location on the ground very, very accurately. So that's it for our radar products and modes and processing levels, and I'll move on to our elevation products. And these elevation products do come from essentially all of our sensors. So on the left-hand side, We have our optical DEMS, digital elevation models, which come in digital surface model and digital terrain model with elevation 4, a 4-meter pixel, a 4-meter ground sampling, elevation 1, and elevation 0.5, which comes from Pléiades NEO. So these elevation models are on demand. We don't have these off the shelf. You do have to come to us with an area of interest, and we can collect the stereo or tri-stereo imagery, and then we can create your digital surface model or digital terrain model for you. So this is more on a local to regional scale. You probably wouldn't want to map an entire country using an optical elevation model. But yeah, from local to regional size, this is the product for you. Getting to our larger scale DEMs, our global coverage elevation models, from Terasar and Tandem, we have WorldDEM and WorldDEM NEO. We have collected the entire Earth, all 148 million square kilometers. We've collected it twice. The first time from 2010 to 2014 with our 12-meter WorldDEM, and then 5 meters from 2017 to 2021. We have a digital surface model and a digital terrain model available, and these are available off the shelf. So you come to us with your area of interest, and we can ship a DEM to you very quickly. One final product we do have is our global radar-derived ground control points. These are 3D points from 30 centimeter to 1 meter accuracy. We essentially bounce a radar beam off a man-made object like a building or even a lamppost, and we're able to give the XYZ location of that object to very, very great precision. So these are, we do have a small database of these, but yeah, we can collect these rather quickly and process these for you on demand. Moving on, just a couple of examples of what these look like. These are the 3 optical modes, from the highest resolution on the left, elevation 0.5, to the lowest resolution, elevation 4 on the right. Those are digital surface models. And just showing off our WorldDEM product here. Here's a WorldDEM NEO DSM. So this is the 5-meter product. So that's the digital surface model, and that's the digital terrain model. So just toggling back and forth for a second there, you can see that with the digital terrain model, man-made features, forests, things like that are removed. So if you're doing flood analysis, you'd much rather have a digital terrain model. If you're looking at signal propagation or something like that, you'd probably prefer a digital surface model. So both of those are available. All right, so I'm going to hand things over to Pete, and he is going to talk about how you access our data using our online platforms. So over to you, Pete.
Thanks again, John. You can move forward from this bumper slide here. So Airbus has developed the next generation geospatial interface and put them all into a single portal that we call OneAtlas. This enables our global network of data users to plan and simulate and schedule the complex observational programs needed to deliver critical geospatial insights every day. So OneAtlas data is basically a unique cloud-based platform where users can access all of our data products. This self-serve imagery platform is available as a web user interface and or via API if you want to work machine to machine. I believe most of the ordering will be done through the CSDA data management team, but CSDA users can use OneAtlas for search and discovery and or ordering if needed. This slide is a snapshot of the OneAtlas dashboard as shown in the web user interface, showing the different imagery services. You can stream and download data from archive. You can task the optical and radar sensors to acquire new imagery over your area of interest, and you can purchase imagery how you need it via subscription or a pay-per-order model. Once a contract is activated, our customers have access to archive imagery, automated tasking, and other data service in just a few clicks within the web interface or the API without any human intervention. We have a dedicated portal for each one. Next slide, John, please. We have a dedicated portal for radar, for optical, and for elevation data. And our satellites are connected directly to the cloud, so you can retrieve the data directly via the portal or API. And the portals are accessible from anywhere in the world and very easy to use. The next slide is an example of our subscription service. Users can subscribe to the Airbus Living Library imagery service. Living Library is simply a curated catalog of fresh, multi-resolution optical archive imagery for instant streaming, as shown in this graphic, where one can view imagery at full resolution, in this case over the island of Mauritius. Users have full access to the extended archive catalog dating back to 2012, and Living Library offers worldwide coverage with daily updates. So this is really premium data sitting in hot storage, which is typically acquired within the last 18 months at very low cloud cover and low view angle. The data in Living Library is available as orthorectified products in bundle or pan-sharpened processing levels, and it can be accessed with very low minimum area requirements. So you can also use the OneAtlas Living Library simply to search and discover our archive assets. This next video shows how easy it is to search and discover our entire catalog over a specific area of interest. In this example, we'll explore some coverage over Iceland. We can search by place name, or you can manually zoom into an area, the peninsula east of Reykjavik here, and users can also leverage the AOI Manager tool to draw a bounding box, a polygon. You can upload a shape file, or you can enter coordinates. We'll upload a 100 square kilometer area here over Grindavik and explore the archive coverage. So the image results will appear on the left. By default, the premium Living Library images result will appear, the 22 images, but you can untoggle Living Library button to view the full catalog, over 560 images here. So you can filter these results by the most recent versus oldest coverages. You can filter by resolution, by cloud cover, or incidence angle, or date range. To explore the assets of the individual archive coverage in more detail, we'll turn on a reduced resolution preview or quick look for this September 7th, 2024 image and view some more metadata like the viewing conditions. We can continue to explore other images like the image acquired on March 23rd, 2024, which has the active lava field. And at this point, you can extract coverages or order the data. Again, most of the ordering will be coordinated through the CSDA data management team, but CSDA users do have the OneAtlas web UI or the API for search and discovery purposes. At this point, I'll hand it back to John to wrap up with some research use cases.
Thank you very much, Pete. All right. Airbus has been in this remote sensing game for so long. We've had so many satellites up there over the years that there are thousands and thousands of peer-reviewed research papers using our data. Articles have appeared in numerous journals. Some of them are remote sensing based, but others are specific disciplines, forest, geomatics, hydrogeology, things like that. So this is just a very small sampling of the sorts of journals that our research has appeared using our data. So we did look at the 6 CSDA Earth Science study areas. These are them. And we did pick 3 interesting examples, 3 papers that used Airbus data that we thought were interesting, just to show off the sorts of things that folks are doing with our data. The first one of these took Pléiades imagery again near Iceland. That's one of our themes today, and they were able to do nearshore bathymetry as the shoreline with earthquakes and lava flows, as the near shore was changing. They were able to look at the water depth down to 28 meters using Pléiades data. So this was a very interesting recent use of Pléiades data to look offshore and see what's going on underwater with our data. Pléiades Neo actually has the new deep blue band. It's one of the 2 new bands that was added. And this one, so here's another example from Yemen, where they're able to use the Pléiades Neo and the deep blue band to do nearshore bathymetry, with the blue being the deepest and the red being the shallowest here. Moving on to a second example here. Here's an example of using Terrasar X imagery to calculate and differentiate different types of sea ice. So here, TerraSAR X images were taken over a variety of different sea ice shelves. And then the folks went out and did the research in situ and were able to validate that, the observations that they made and the calculations that they made were able to provide good correlation with their on-site measurements. Here's another example of using TerraSAR to monitor sea ice. This was one of the world's largest icebergs in 2017 as it broke off from the Antarctic ice shelf. And here it is at the end of 2018 as it pivoted and started floating north. So here's an interesting way that people can track in very, very remote areas what's going on. And TerraSAR X, it's a radar satellite. It's completely cloud-free. So it's always going to give you an image, even in the Antarctic winter, things like that. And our final example here, this is an example where researchers took our stereo imagery from Pléiades and made their own elevation models. So we can make elevation models for you, but you can also take stereo imagery and make your own elevation model. And here they were able to make this elevation model of a new bridge under construction in Canada, in Montreal, and they were able to overlay that on SRTM. And they discovered that it significantly improved their accuracy rather than just using an old elevation model by itself. And one final example, just showing how here in much further north in Canada, WorldDEM can serve you because we do have, if there's land, we have WorldDEM for you. It is available completely globally everywhere. All right, that is our final slide, and we end where we started in Sydney, Australia, with a famous opera house you might have heard of. And we'll move on to the questions, but here in the final PDF, you'll have a link to our CSDA page, a link to our sample imagery. This is free imagery that's available to everyone, and all of our Airbus product specifications and data sheets are linked from there. And of course, the names and email addresses of our presenters today. So thank you very much for listening, and I will hand it back to Jennifer at NASA, who I think is going to curate the questions for us.
Yes, thank you so much. Okay, so why don't we go ahead and get started here. I am going to start with the Q&A panel, and then I'll jump up to the chat to make sure I have also captured those questions as well. Okay, so let's see. Dana, if you could verbally address the question that was asked early on, is the Airbus optical constellation data currently included in CSDA? That would be helpful. Just reiterate, what you have provided in the chat. That would be great.
Sure. So as part of Airbus's IDIQ contract, they have offered the optical data to the CSDA program. You currently cannot see it as part of our existing available data to stakeholders because we haven't purchased the data yet. And that's why you don't see it either in the SDX or the website. Once the program decides to purchase that data, then it would be made available to the broader stakeholder community.
Thank you so much, Dana. Okay, let's go ahead now on to the next question here. Okay, and we may need additional information from this participant, but the question was, what is the registration accuracy and precision in absolute and pixel relative versions? And so you may need
to take that.
Okay, go ahead. That'd be great.
Yeah, we might need a little bit more color there to address it, but we do offer the geolocation accuracy for each of the sensors on those specification charts. We offer statistics on both absolute and relative accuracies. But speaking in general terms, we calibrate our satellites routinely. We perform absolute radiometric monitoring and calibration, and we even do consistent cross-calibration between SPOT, Pléiades, and Pléiades Neo. We use in situ acquisitions. We use the moon, the stars, to perform these routine calibration activities. So we take a lot of pride in the high quality and the accuracy of our products. So when it comes to native geolocation accuracy, those figures were presented. When it comes to planimetric accuracy, we use in-house DEM and ground control to produce ortho products with an absolute geolocation accuracy. And we can bring it down to the pixel level with perfect DEM and perfect ground control.
Well, thanks so much, Peter. And actually, this next question was a question specifically for you. Excuse me. Are there routine passes that the SPOT and Pléiades are collecting persistently, collecting pre-incident and post-incident information for disaster response would be most useful?
Yes, certainly. We do a lot of programmatic acquisitions, covering current affairs, global disasters, but essentially our customers are tasking the satellites on demand. So we're collecting where customers are asking us to collect, but there are programmatic acquisition activities where we're collecting imagery over a specific region of the world to update our base maps. But yes, we can collect daily at a global level. So we can collect pre-event and post-event, depending on the weather, of course. So we have tasking options. I touched on to the two of them. With one day, we can collect on a specific day. With we also have another tasking option called One Now, where we can turn on the sensor and we'll just start collecting until we get usable imagery. And then there's that one plan collection option where, you give us your AOI and we'll collect it based on your parameters as soon as possible. But yes, we do collect a lot of pre-event and post-event imagery throughout the year.
Well, thanks so much, Peter. The next question is regarding the image of the Statue of Liberty. Was the image enhanced using deep learning-based super resolution?
Yes, exactly. So we're using in-house technology. It's a deep learning AI model, and we're leveraging very high resolution data as a reference. So yes, it is a super resolution, that HD15 product.
Okay, well, thanks so much again. And the next question is the TerraSAR X ScanSAR data acquired with burst synchronization between passes?
Sorry, I need to hear that one more time.
Absolutely not a problem. So the question is the TerraSAR X ScanSAR data acquired with burst synchronization between passes?
Burst synchronization. I do not know the answer to that question. I will have to get back on that one. Sorry, that's a little too deep for my technical knowledge of the hardware.
Well, that's okay. So Eric, we'll have our speakers get back to you offline. And thanks so much for that question, by the way. Okay, so the next question coming up here, bear with me for a moment. Okay, is there published information on how Airbus extracted the DTM from the WorldDEM? So any data set documentation or other data documentation for those products?
I would have to look it up. We might have put out a paper or two, but yeah, it's a relatively simple way of identifying the objects that protrude above the ground, and there's a segmentation that's done, and then the objects that project above the ground are removed using a variety of algorithms. If it's short. If it's a short, narrow feature, then it's just interpolated right across. If it's a large area, like an enormous closed canopy forest, we use shifting, which is pretty much the standard way of doing this, where we shift the entire forest elevation down based on forest height measurements. So I would have to double check whether there's anything published on that, but it uses pretty standard algorithms for detecting objects that protrude above the ground, segmentation, and then eliminating either via interpolation or shifting the very, very large objects. That's the brief summary of how it works. I will double check to see if there's anything published describing that process.
Okay, well, I appreciate your response, John. And moving on to our next question here, what is the process for requesting Airbus optical imagery, for example, found via OneAtlas via CSDA, and is tasking through CSDA a possibility? So maybe Dana or Aaron from the CSDA program, if you'd like to weigh in here.
Sure, I can take that. So if there's some interest in the optical data, I would suggest reaching out to the CSDA program. You can email myself or the program manager at headquarters, Melissa Martin, and we can put my email contact in the chat. We can take it from there at that point.
Okay, thank you, Dana. So let's see here. Okay, sorry if I missed this. What are the spectral bands of your optical satellite products?
I can take that one. So SPOT and Pléiades are 4-band. They're red, green, blue, and near infrared. The Pléiades Neo is 6 multispectral bands. We added the red edge and the coastal blue. So SPOT and Pléiades are 4-band, the standard 4-band, and Pléiades is 6-band.
Okay, and just as an FYI, you have stopped sharing your screen. Oh, there we go. Perfect. Okay, thank you.
Exactly. Yeah, that'll be listed in the final PDF there. So you can see the spectral bands and the spectral ranges for each of the satellites. Pléiades Neo being the 6-band option here with the red edge and coastal blue. And then Pléiades 4-band with the spectral ranges shown there. And then SPOT, also 4 bands, multispectral bands listed there.
Okay, excellent.
And we can produce just the panchromatic deliverable or just the multispectral deliverable or just a bundle or a pan-sharpened product combination.
Okay, thanks so much, Peter. And we can put the link to the user guide in the chat another time here as well. Let's see. Just want to make sure that I haven't missed any. All right, so the next question is, and then I'll double check the chat. Okay, there's a comment combined with a question. My team runs a cloud-based computational platform where users, other researchers, can run models and access data. What is the procedure to allow our users to access CSDA Airbus data?
Dana, did you want to handle that question?
I'm just rereading. So it depends. So right now it depends on how the data is being purchased, what kind of end user licensing agreement it is purchased under. I would suggest reaching out to us at CSDA just to talk about a little bit more about how you're funded, the program's funded, and who are the researchers the data is being provided to, and then we can kind of talk from there.
Okay, thank you, Dana. All right, let's see here. Let me scroll back through the questions and the Q&A. And while I'm doing that, I just wanted to make a point to let everybody know that today's webinar has been recorded, and the webinar will be posted both to the webinar event page on earthdata.nasa.gov. If you click on Learn in the top menu bar, and then webinars, you'll see that the CSDA event for today, I think, is the second event that's listed. And so I'll post the recording link there. I'll also follow up via email with the recording and presentation slide decks links. And then also they will be on our NASA Earth Data YouTube channel within the CSDA playlist. And in a moment, I can place that link in the chat for everybody if you are interested. Let's see here. I want to make sure I didn't miss anything in the chat. I'm still just going through. And just a comment for everybody, in case you're wondering why we were placing all of the links that correspond to the content in the slides as we go through. Over the years, we find that it's helpful to include those links concurrently with the content being presented, or at least as close as possible, for those users who may have missed the link to the presentation itself. So hopefully most of you find that information useful. I'm looking again. Let me go down to the Q&A to see if there's something else. I am not seeing any additional questions. We'll give it, we've got like 3 minutes left in the extended Q&A. So what we will do today, if there are no further questions, we will leave the virtual meeting space open for an additional 10 minutes from end time. And I will close the audio component, but I will leave it open just in case you have any questions that you'd like for us to forward along to the CSDA program speakers or team members that are on the call today, as well as any questions for the Airbus team. Okay, so thanks so much to all of you. I'm going to do one more quick check and see here. I don't think I've missed anything, but if I have and you're still online, please feel free to correct me by reminding me of your question if we did not get to it. But I believe we've covered all of the questions. And I want to just thank all of you for joining us this afternoon, and thanks to our speakers, both from Airbus and also from the CSDA program. Again, I'm not seeing any additional questions here. All right, everybody. So with that, thanks to all of you for your participation this afternoon. And our next CSDA program webinar will be held on March 19th, and will focus on GHG-SAT's data sets, services, and tools that are available through the CSDA program. So thanks to everybody. And with that, we'll leave the audio. We're going to log off from the audio component, and we'll leave the virtual meeting space open. All right. Have a wonderful afternoon.